Hey, welcome back. This is 11.3 on the dot product. So this is a first kind of attempt at multiplication of vectors. We're going to have two different kinds of products, the dot product and then the cross product. The big difference is that the dot product is a scalar. Okay, so first, just how do I get the dot product? So our first example here, u, let's say, is 3, 4. V, let's say, is -1, 5. To get u dot v, all you need to do is multiply the first component of each. So 3 times -1 is -3. And then add it to the product of the second components. So 4 times 5 is 20. So that would be 17. And that's it. I mean, that's as easy as it is. If we had, let's say, some other guy, 3, 4, 1, and then maybe some S vector, -2, 1, 0. Same idea. W dot S would be -6 plus 4 times 1 is 4 plus 1 times 0 is 0, and that would be -2. Okay, so no big deal. There's some cool things about these guys. For example, u dot u. How would I do that? So it would be 3, 4 dotted with 3, 4. That's just going to be 3 times 3, which is 9, plus 4 times 4, which is 16, which is equal to 25. So compare that then. So note the magnitude of u squared. What is that? So the magnitude of u would be the square root of 3 squared, which is 9, plus 4 squared, which is 16. And that would equal, and we're going to square that, and that would equal the square root of 25. So if you square that, you get 25, which is exactly equal to u dot v. Okay? It's that sort of acknowledgement which becomes important later here when we're doing the interpretation of the dot product and working with basically the angle between these two vectors. So one way to think of the dot product geometrically is to consider it as a measure of the alignment between the two vectors. So that could be important if you're talking about sort of a membrane, and maybe you have blood going through the membrane and you want to know how much is the blood, how much blood is going through the membrane. It would be dependent on the direction of the blood. Is it going perpendicular to the membrane? Is it going in the same direction as the membrane? That sort of thing. So it becomes important later. Anyways, there's going to be a bunch of kind of properties of the dot product, just like we had with properties of vectors before. So this is from theorem 11.4. And you have, your basic ones like the commutative property of the dot product. U dot v is the same as v dot u. There's kind of a distribution law. So u dotted with v plus w would equal u dot v plus v dot w. So some of them, are there to help with the proofs that we go through. Some of them are helpful to reduce the number of computations that you're doing while you do your homework. Okay, probably the one that's important in the proof we'll see later is this guy, the number 5. So you could rewrite the square of the magnitude of the vector as a dot product. Okay, let's prove number 5 while we're here. So suppose that we're working in the plane and our vector v is equal to v1, v2. We want to show that v dot v is equal to the magnitude of v squared. So usually what happens in these kind of proofs, we want to start on one side of the equation and then use algebra, definitions, substitutions, properties of real numbers in order to get to the other side of the equation. So let's start on the left-hand side. We note v dot v from substitution. We could write that as v1, v2, dotted with v1, v2. And then from the definition of the dot product, that's just equal to v1 times v2, or sorry, v1 times v1 plus v2 times v2. We could, of course, rewrite that as v1 squared plus v2 squared. And then that's the same as the square root squared of v1 squared plus v2 squared. That's just basic algebra. And then we could do a substitution with the magnitude, right? So the square root of v1 squared plus v2 squared is just the magnitude of v. And then we got to the right side of the equation that we were trying to show. Okay. Okay, so anyways, there's that. Let's move on to kind of more of the geometric interpretation of the dot product. And in particular, we'll introduce the this angle between two vectors kind of relationship. So section 2, the angle between two vectors. And we get this formula, and there's some sort of restrictions. So given two non-zero vectors, let's say u and v, such that the angle between the two vectors is between 0 and pi, then we can make a relationship between the dot product and that angle via trig. So cosine of theta will equal u dot v, all of the magnitude of u times the magnitude of v. Okay. The proof of this thing follows from the law of cosines. We can obtain this formula. I'm not going to go through the whole proof, I'll just kind of set it up through the law of cosines for triangles, which you probably learned in trig and already forgot, but formula through the law of cosines for triangles. So notice this picture of the two vectors here, say u and v. You could form a triangle by putting a third vector on here like this. And of course, when you connect the two ends of the vector, what you're looking at is the difference of the vectors. So this vector is v minus u. And then if you have the magnitude of the three sides of the triangle, you can relate all of that to the cosine of that angle using the law of cosines. So the magnitude of the side opposite of the angle squared is equal to the magnitude of this one side, adjacent side to the angle squared, plus this other side, which is adjacent to the angle squared. Is it minus or is it plus? I think it's minus 2 magnitude u, magnitude v, cosine of theta. Okay. So you're going to be able to make this relationship by noting that one, this fifth point from theorem 11.4, you can use that to replace the magnitude squared, and then you could solve for cosine theta, and you end up with the formula we're after. And you can see the proofs in the book. I'm not going to go through it. Okay. So some magic happens, and you end up with cosine of theta equaling u dot v all over magnitude u, magnitude v. Okay. With all the little arrows. Okay. So this, you know, you could use this in any form. You can multiply both sides by the magnitudes, solve for u dot v, and then you are able to kind of make some statements about the relationship between the two vectors with regards to the dot product. So alternatively, sorry about my spelling, okay, so alternatively, we could solve for u dot v, and then we have our nice relationship between the dot product and this angle theta. So geometrically, if your vectors are completely going in opposite directions, the angle between those vectors will be 180 degrees. So u dot v will be negative first off. So if you have a dot product that's negative, you can assume that the vectors are going in opposite directions, and it'll be maximum when the angle is exactly 180 or pi. Okay. When the two vectors are orthogonal or perpendicular, that's the angle between them will be 90 degrees or pi over 2. And in that case, guess what? The dot product is 0. So it becomes a diagnostic for determining if your vectors are orthogonal. Finally, if the vectors are going in the same direction, that's when the dot product will be a maximum. Okay, so u dot v will be equal to magnitude of u times the magnitude of v. So cosine will be exactly equal to 1. I do a nice little picture there in the book. I basically just reproduced the picture for you. Okay. Okay. And then they note, I think orthogonal, perpendicular, normal, they all mean the same thing. So you're probably not used to hearing orthogonal or normal, but that's what we're going to call them in the book. Okay, let's look at some generic kind of example problems, like in homework. So, for example, find the angle between the two vectors. So we have u is given as 3i plus j, and then v is given as negative 2i plus 4j. Okay. You could spot check it to see if they're orthogonal. In this case, they're not, right? It's negative 6 plus 4 is negative 2. They're kind of going opposite directions. So what you do then is go to your cosine theta formula. So cosine of theta is equal to u dot v all over the magnitudes, and then figure that out and take the cosine inverse of it. Okay. Okay, so cosine of theta is going to equal the dot product, so 3 times negative 2 is negative 6, plus 1 times 4 is 4, all over the magnitudes. So 3 squared plus 1 squared is 10, and then negative 2 squared plus 4 squared, that'd be 4 plus 16 is 20. And then, let's see, let's go down another. So I have cosine of theta is negative 2 all over the square root of 200. Take cosine inverse on both sides. And then go to your calculator to get your approximation. Make sure you're in decimals. And it's approximately 98.1 degrees. So more than 90 degrees. So they're kind of going in opposite directions. Okay. There'll be questions where they're trying to get you to figure out if it's parallel, perpendicular, or neither. And usually you just hope that the things are perpendicular, because the dot product will let you know quickly whether they're perpendicular. And of course, to find out if they're parallel, you just see if they're multiples of each other. So it's the neither that you want to watch out for. If it's neither, you have to go to what we did with the cosine theta formula. Okay. But anyways, let's look at these guys. So it looks like they're probably orthogonal. Do a dot product, see if it's 0. So 4 times 1/2 is 2. 3 times negative 2/3 is negative 2. That's equal to 0, so sure. A quick way to produce orthogonal vectors, if you didn't already figure it out previously, so let me say quick way to get orthogonal vectors, and this only works for vectors in the plane. This won't work for, I can't think of a quick way to get the orthogonal space vectors. But if you're given u equals 4, 3 to get an orthogonal vector quickly, all you got to do is swap the components and make one of them negative. So you go 3, -4, or you can do -3, 4, or you can do multiples of those, right? So that vector that we saw on this problem is just a multiple of this vector here, right? Because what would it be? 1/6 times that vector is so 3/6 is 1/2, and then -4/6 is -2/3, right? So you know that sort of becomes an issue later because we have to quickly figure out these. So when you're working with a trajectory of some object, at any point, it's nice to know the vector in the direction of travel, but also the vector that's orthogonal to the direction of travel. Okay, and we'll call that the normal vector, and it can go point inside or it can point outside. Usually, we want it pointing inside. Okay. The next part is on projections. And this comes up, this is useful in physics. So there's an alternative point. We're not going to do the direction cosines. You can go ahead and do that if you want. It's just it never comes up again in the rest of the book, so I'm not going to bother. And I didn't put it in the homework either. If you feel like you're missing something, you can go ahead and do it on your own. Okay. All right, so anyways, projections of vectors, important in physics. You'll see it in your physics book. You'll have to figure out stuff like this. The force orthogonal to the ramp, the force that you need to keep the boat from rolling down the ramp. And we also need it for figuring out work. So anyways, let's look at the projections now. So section 3, projections, and the vector components. Okay, so the scenario is you have some vector here, and you want to figure out its projection onto some other vector here. Okay, let's call this vector v. So the projection of that u onto v is going to be this red vector here. And then there's also this other vector, we'll call this first vector w1, and the second vector w2. Okay. So W1 officially is going to be the projection of u onto v. Projection, we write it like this, u onto v. And then W2, you can kind of get W2 just noting that W1 plus W2 is equal to u. So W1 plus W2, and these are vectors, by the way. Is equal to u. So W2 is easily found if you know u1 and w1, or if you know u and w1, like that. Okay, so we need a formula for this, and we're going to be able to use this angle here and a little bit of a trig to figure that out. So the way we will get the projection is to first resize the vector v into a unit vector. So first we can kind of resize vector v. So to get into a unit vector form, we'll take v and divide it by the magnitude of v. Okay. And then we want the magnitude of the resulting vector to be the length of w1. Okay. So to find the length of w1, we can use trig, right? So we notice that the cosine of the angle between the vectors is going to be equal to the magnitude of w1, which is what we're after, divided by the magnitude of u. So basically adjacent over hypotenuse. Then you could solve for the magnitude of w1. So that'll be magnitude of u cosine theta. And then you could use all of our cool cosine theta formulas, dot product formulas, to rewrite that as a dot product. So noting our relationship that u dot v is equal to the magnitude of u times the magnitude of v cosine theta, divide both sides by the magnitude of v, and flip-flop sides, and you get that the magnitude of u is equal to u dot v, the magnitude of u cosine theta, cosine theta is equal to u dot v all over the magnitude of v. Okay? And that's the thing that we want kind of as the scalar in front of the unit vector v over magnitude v. Okay, so hence the projection of u onto v is going to equal u dot v all over the magnitude of v times this unit vector. Okay. And then we could shuffle things around a little bit and rewrite it as u dot v all over the magnitude of v squared. Is kind of your scalar in front of the vector v. Okay. Okay. So let's apply this then to braking load. So one thing to notice is I often like using the projection formula in this form, in particular because I could figure out the magnitude of the projection if I just get this thing right here, because the magnitude of that v over magnitude of v is just 1, right? And then we know that the magnitude of a constant times a vector is equal to the absolute value of that constant times the magnitude of the vector. And if the magnitude of the vector is 1, then the magnitude of that projection is just going to be the constant. Okay. So hopefully that won't be too big of a headache. It's kind of annoying, but let's take a look, okay? So we can look at the example from the homework, this problem with the truck. So I have some sort of truck going up a hill. And it weighs a certain amount. The hill is at an angle of 10 degrees. And they want us to find, what do they want us to find? The force required to keep the truck from rolling down the hill, and then the force perpendicular to the hill. Okay? And believe it or not, this is a projection problem. So first thing I'm going to do is kind of reorient things. I like to do this. You may not necessarily agree, but what I'm going to do is put the truck here at the origin, and then here's the hill. And this is 10 degrees, and then this will also be 10 degrees, right, from geometry. The weight of the truck is 48,000 pounds, so this force vector right here on the truck is going to, if we call it F, we can actually write out the vector in its component form. So it's going to be 0, negative 48,000. Okay, so we have the direction, and if we took the magnitude of that, we would get the 48,000 pounds. in order to figure out the force required to keep the truck from rolling down the hill, what we're after is the projection then of that force vector onto the hill. So it's this vector would be your W1 vector. And then the force perpendicular to the hill would just be your W2, this vector right here. So let me extend my force vector down like this. Okay. So this is F, and this guy would be W2. Okay. You got to be a little careful about how you do your vectors. So you could say W1 is just cosine 10, sine 10, and have it magnitude 1. The problem is the projection is going to be negative. So you got to be a little careful. Usually it just comes down to if you get a negative for your answer, make it positive. Take the absolute value, because your problem is you've forgotten to take the absolute value of the coefficient from this formula here. Okay, so let me give my W1 vector. So I'm going to go ahead and, instead of using cosine 10, I'm going to use, excuse me, this angle here, which is 190. But like I said, it would still work out the other way. It's just you'd end up with a negative for your projection. Okay. So these are it's pretty hard to screw it up, really. You can almost randomly kind of blindly do your way through the problem and probably get it right. But anyways, here we go. Cosine 190, sine 190. So I want to find the projection of F onto this vector W. So it's F dot W all over the magnitude of W squared times, that would be your constant, and then times the vector, this would be your scalar times the vector W. That denominator is just 1, because W, the way I've done it, is it's a unit vector, right? Because you get the square root of cosine squared something plus sine squared something, which would equal 1, right? From our Pythagorean identities, that's equal to 1. So that thing in the denominator is just 1. So all I have to do is get the dot product. That will be 0 times cosine 190 is 0, and then negative 48,000 sine 190 times our vector for W, which is cosine 190 sine 190. Then to get the magnitude of the projection, rather than distributing this constant into the vector, let's just use our relationship up here. You could take the absolute value of C and then just find the magnitude of this thing, which we know is 1, right? So it's just the absolute value of negative 48,000 sine 190, times the magnitude of this thing, which is 1. So really all you have to do is find that thing. So negative 48, maybe just do 48,000 times sine 190. So it's 8335.11 pounds. They only want 1 decimal in the actual question. So that's part A. What we just did, we found the force required to keep the truck from rolling down the hill. Okay. The other case, then we need W2 to find the force perpendicular to the hill. So part B, find. And again, this is the video quiz question. This example is the video quiz that you need to basically just copy out. And this will be, what is this, the 3rd video quiz question? Yeah. So usually turn in 4 video quiz questions at once. Yes. Okay, so part B here, we want to find the force perpendicular to the hill. Again, this is the video quiz question. This is the video quiz question. This is the video quiz question. Find force perpendicular to hill. Okay, so now we're going after that other component, W2, and W2 is going to be the difference of, how did that work? So W1 plus W2 equal the, let's go back and look at the picture. W1 plus W2 equals F. So W2 is going to be F minus W1, and then we're going to need the magnitude of that. Right? So anyways, F we figured was 0, negative 48 grand, minus W1, which we just figured to be, it has that ugly coefficient on it. So negative will be plus 48, 1, 2, 3, sine 190 times cosine 190, sine 190. Again, I think what we'll end up doing here is factoring out anything we can. So anyways, it's going to be 48, 1, 2, 3, sine 190, cosine 190, comma, and all I'm doing is adding the components, right? Plus that part after I distribute that. And then the second guy, negative 48,000 plus 48,000 sine 190, sine 190 squared. Okay. So I need the magnitude of that guy. What I'm going to do then is just pull out the 48,000, make my life easier. Can I pull out anything else? Nope. So sine 190, cosine 190, comma, negative 1 plus sine squared 190. And then the magnitude of W2 will be 48,000 times the square root of all that junk squared. Right, so sine 190 cosine 190 squared plus negative 1 plus sine squared 190 squared. And then I got to go to my calculator and figure that out. Right? Okay, so calculator on. I'm just going to figure out the square root part first. So square root sine 1. Oops, this is going to be hard because all the parentheses. Sine. Make sure you're in decimals. Sine 190 cosine 190 squared plus negative 1 plus, and then I got to square the sine 190 squared and squared in parentheses. Okay, so I'm getting about 0.9848. I wouldn't approximate until you're done, because the computer won't, if you're off by like 1 decimal, the computer will mark it wrong. Anyways, just for me showing you what answers I got, I wrote it like that, and I'm just going to multiply in my calculator by 48,000 without approximating, and I get approximately 4720.77 pounds. Of course, I rounded 1 decimal in the homework. Okay, so there's that. The last thing we got to worry about is work, because we will be evaluating work later on in vector calculus with integrals. Block work. So it's pretty easy if the force is in the same direction. So what's going on here is you're pulling like a wagon or something like that, and you're going from some point, we'll say A, to some other point B. It's easy if you're pulling completely straight, because then it's just going to be the force times the distance traveled. What's hard is when you're pulling like you normally would at some angle, right? Then it's going to be the magnitude of the projection times the distance traveled. Okay, so work will be equal to, in general, we'll just say force times distance. But like I said, it's the projection of the force when you're pulling at an angle like that. So we'll say work is equal to, and let's call this AB, let's turn this into kind of a vector. Let's call this the AB vector. Let's call this vector force vector, like that. So work will equal the projection, the magnitude of the projection of the force onto this direction vector times the magnitude of the direction vector. And then we could use all of our nice little identities with cosine theta from above to get different forms for this work. And usually the problem just come down to picking the most appropriate form for the question that's given. Okay, you even get a little wagon problem in the homework. So yeah, remember the magnitude of projection is just the junk in front of the v over magnitude v. So again, if you look back at our work with projections, I don't know where it is. Hope this ain't making me dizzy. It's this thing I circled in red is the projection, the magnitude of the projection. So it's u dot v over v, or in our case, it would be f dot ab all over the magnitude of ab. Okay. And then if you multiply that by the magnitude of ab, the little magnitude ab's cancel, and you see that work is really just a dot product of f dotted with the direction vector. Okay, another form they will also use is noting, so how did that work? So f dot ab, recall, is the same thing as the magnitude of f times the magnitude of ab, cosine theta, cosine of the angle between the two vectors. So we could rewrite the, f dot ab then as the magnitude of f times the magnitude of ab times cosine theta. And you could also use that form if you want, which is probably what they're doing in this question with the toy wagon. So hey, let's try the toy wagon problem, right? So the toy wagon is being pulled by a force of 50 pounds. So, and it's making an angle of 40 degrees with the horizontal. So we could get our force vector to be 50 pounds, sorry. So 50 cosine 40, comma 50 sine 40. And then find the work done and pulling the wagon 20 feet. Okay, so, I mean, you could get it like this. You could just say the magnitude of the force, which is 50, times the magnitude of the distance, which is 20, times cosine of the angle between the two vectors. And I think that'll do it, right? So let's see, 50 times 20 times cosine 40. So it just turns into like a plug and chug, if you know the formulas. Usually I'll give you kind of a formula sheet with some formulas on there, and from the formulas that I give you, you should be able to derive the other formulas. But we'll cross that bridge when we get to it. Anyways, I think that'll do it for this video. I'll call it quits. I think I got everything that we really need to talk about. There's the boat problem, and then the force problem, work problem, and then homework. Yeah. Okay. So as usual, thank you for watching, and I'll see you next time.